All right. Hey, everybody. If you can make your way back to your seats, we are going to get this thing rolling with our very next talk. So our next speaker is Ryan Betts, who joined us just under a year ago. Ryan used to be at VoltDB, where he was the CTO. He worked with Stonebreaker back in the day. Stonebreaker of database fame, and now Ryan Betts of database fame, is going to give a talk about the internals of InfluxDB. So please welcome Ryan to the stage.
Thank you. Well, today's been great so far. I think so. I'm responsible for the team that builds InfluxDB and Capacitor. That's my role at Influx. This morning, Paul told me what he wants me to build, and then right after that, Colin, I think, told me what I should build. So it's been a great morning. I'm going to talk about databases. I have a theory I'm going to test out. It's the first time I've done this poll. Who thinks databases are great? Like, who loves databases? Who gets up in the morning and says to themselves, I want cereal and a database, right? I'm kind of that way. Now, who actually runs and operates databases? Oh, okay, it's an intersection I didn't expect to find. I was pretty sure that it was either one or the other. So I've been working on high-speed data for about the last 10 years or so. A lot of this presentation is really due to the credit of the team that I had the pleasure of working with. These are things I've learned as I've asked them millions and millions of questions over the last few months. And I thought I would try to put together some content that explained a little bit about the internals of Influx. So I want to talk about three things in particular today. What's so special about time series? Hoping this is an easy sell to this crowd. A little bit about time series database design, some different ways that people have specialized databases to manage time series, and sort of a tour through some of the major internal components of InfluxDB that I hope I can make approachable on slideware that have been helpful to me in understanding sort of how to mentally model and think about the performance and what Influx is good at and what it's bad at. So databases are conceptually really, really simple. Like, all you have to do is write something down and then read it back later, right? It's pretty straight ahead. It turns out, however, that these two simple ideas are really in incredible tension with each other when you design a database. If you want something to be really easy and efficient to read back later, you have to do a lot of work when you write it down, right? Like, remember where it is, build an index, put it in some kind of an order, right? You have to do something to make it easier to read. If you make it really easy to write data down so that you can receive it really quickly, it in turn becomes really difficult to read back, right? You don't know where to find it, it's not organized, hasn't been pre-processed, hasn't been filtered or anything like that. So really, everything about database design is trying to take these two simple concepts: how do I write something down, how do I read it back, and trying to think like, well, what trade-offs can I make for my domain to simplify the tension between storage and query? That's kind of all there is to it. However, you can see that there are, I don't know, maybe 1,000 databases out there. Probably over the course of this talk, someone will write another time series database. I don't doubt it. It seems to happen about once a week. At least they start. I don't know how many finish. Probably none of them finish. So here's just a couple of different categories of trade-offs that can be considered. Correctness, schema. Is your schema pre-declared or not? How do you write data to the system, and how do you read data, right? So it's really like top-level, pretty generic concerns that every database has to have an answer for, and a couple of different types of answers that different systems give to these simple axes. So the relational database management system, like kind of the traditional databases, MySQL, Postgres, Oracle, Oracle's row stores, they make a pretty, what we think of, I think, traditionally as database choices. For correctness, they're transactional, they offer consistency, they offer durability, separate actions of different users through isolation. For schema, they have DDL. I think it's actually interesting here to think what DDL means, data definition language. Right? They're actually providing a set of rules that describe what's legitimate data and what's not. You can have complex foreign key constraints, uniqueness constraints that are actually embedding business logic directly into the definition of the schema itself. For writing data, you take a transactional approach. For reading data, you can use SQL. NoSQL systems, kind of looked at this and tried to gain some more flexibility. So for correctness, they chose basic availability and soft state or eventual consistency, kind of whatever language you prefer, over ACID. Some have actually moved more towards data definition, again, like Cassandra, but many are still document oriented, where the user's defining the shape of the data as they insert it. And they've relaxed, in many cases, the richness of ingest and query capability for performance and scale. Time series databases, I suppose, could be a category of NoSQL, but I think deserve to be a category unto themselves because they're really exploiting aspects of time series data that's unique and that's not shared across, for example, an operational store where someone's using a NoSQL system as a profile database for users or an inventorying system. So what are the choices that can be exploited by a time series system? And really, if you start to think about these, are they unique enough to create a category of databases specialized to this purpose? And I think we see that they are. So for correctness, time series systems certainly favor availability over perfect transactional correctness, right? They're eventually consistent. You want to be able to write data freely, even if it's not available for immediate consistent query. And you want your database, especially in a monitoring context, to be able to return best effort reads even if not all of the data is available. Especially in monitoring use cases, we don't care always about each iota of data, right? We're often just batching and trending, although Colin had some great use cases where individual points do matter. But in this case, there's many places where you can exploit the fact that not every unit of data is immaculately important, right? Sometimes it's the aggregation that matters more. Time series databases are integration points. You roll them out into an organization. You want to make them easy to consume. And so you don't want to put a barrier for someone introducing new data on the developer that wants to use the database. And so in this case, time series databases have this nice advantage. We kind of know what we want a metric to look like. It probably has a name, it has some attributes, it has a value. So there's kind of this implicit shape already of what a metric looks like, and we can use that to allow developers to essentially create a schema when they introduce a new point or a new series to the database. So we can kind of create this nice mixture of schema that gets kind of instantiated on write. And then on the read side, unlike a lot of NoSQL systems, time series systems are analytic systems. Really, the value to the user is how much analytic can you do, how can you query, how can you shape this data, how can you filter this data, and you end up doing a lot of filtering, windowing, grouping, joining, things I'm sure you're all quite familiar with. So you need a way to store data that enables these very rich queries. So time series databases really end up with a unique combination of requirements. You want to be able to ingest thousands to millions of points per second. You need to be able to store data that's fast accumulating and append mostly. Oftentimes there's a lot of repetition in this data, or like values that are typically 0, typically 100, timestamps that are incrementing slightly. You can exploit those patterns of data for very nice compression techniques. You want a very rich query interface. This is absolutely key. You can't have a useful time series database if you could only retrieve one point at a time, for example. And you need to be able to scale this time series system along 3 different axes. You need to scale it for availability. Right? You want to replicate the data in the database so that it's available in the case of failure. You want to be able to scale it for storage so that you can store more and more data at finer and finer granularity without forcing rollups. And you want to be able to scale query efficiency across this data as well. So when you look at these 4 primary requirements, I think you start to see different trade-offs that you can exploit to make a system that's excellent at time series data. So there are a number of time series systems that we can look at that are pretty cool. I think I'm not sure who's here. I'm not really quite sure who's in the audience. So who here knows like the Gorilla paper? Who kind of is really familiar with some of these things? All right. So the Facebook Gorilla paper is really cool. It kind of it's one of the monitoring systems that Facebook uses that they've written about. And they first published this paper at VLDB, which is a very large database conference, really cool database conference. If you love databases, go to VLDB. It's really fun. They kind of talk about some of the trade-offs they made. So the Gorilla is a fully in-memory system. It runs on a couple hundred servers with many terabytes of RAM cumulatively. It does time-based eviction, right? So it kind of keeps the most recent data in memory. It uses a lot of columnar compression. I'm going to talk a little bit about how InfluxDB does columnar storage. So if that's not a familiar term, we'll talk about it a little bit more later. It favors write availability over query correctness. It has a metric-based schema, right? Users can write basically a metric name and a value to it. So it has kind of an implied shape of data, but users can make up new metrics on the fly. And it separates its query processing from its access path. So it's kind of fancy database words for basically saying that the database is responsible for returning the appropriate data but the actual querying happens off in rich client libraries elsewhere. So you actually start to see this trade-off a lot of places in time series databases where you want to be able to have a system that can efficiently access and filter and return streams of information that are relevant to you, but you'd like to be able to push the processing of that off to CPUs that aren't pegged to those storage nodes. This is for a large number of reasons. You have many different types of query tasks that run against a time series system that kind of argue for this separation. You have dashboards that are repeating the same queries over and over that might be quite small, but then you also might have a data analyst that's trawling through a vast amount of history. You'd like to be able to provide priority to those different queries. The dashboard queries need to be returned like relatively quickly, at least within the update frequency of the dashboard, whereas some of the longer running analytic queries can run in the background and kind of run in the gaps when the dashboards aren't being filled. So it's nice to be able to have CPUs that you can dedicate to these different purposes that aren't also responsible for the ingestion and compaction and organization of data on disk. So here you can see that example, and you can start to see a little bit of how at Influx we're moving in that direction with some of the work that Paul was talking about with IFQL. Druid is another popular analytic system that's often used for time series data. You can see that it's also making some of the similar engineering choices. Druid has the ability of doing roll-up of data at ingest. Again, Druid is storing data in a columnar format for very nice compression reasons. It includes the ability to index on dimension data, kind of like Influx indexes on tags, so that you can find different series or different measurements quickly that meet a certain criteria for a tag filter. And it has also this concept of separating real-time nodes from historical nodes and query nodes from storage nodes. Right? So you kind of again see the separation of concerns, try to make the system flexible at scale. I have another favorite time series database. I think this is actually probably the world's most popular time series database. How many people here are know bullet journaling? Okay, how many people here follow bullet journals on Instagram? Yeah, all right, maybe I'm telling you a little bit too much. So bullet journaling is, the metaphor doesn't quite work if you're not familiar with it, but we'll walk through it because it entertains me, at least. So a bullet journal is just a very simple sort of journaling technique that I think someone named Carol Ryder came up with. And if you understand sort of the different aspects of bullet journaling, you'll really understand how to write a time series database. Like everything you need to know about designing a time series database, you can get from the 5-minute talk that he gives on how to write a bullet journal. So the core concept of a bullet journal is you want to make it really easy to write tasks down, right? So every day, you just start a new day, and you just basically write out a to-do list for that day. In database land, we call that really fast ingest of thousands to millions points per second, right? Bullet journal is just like, I want to quickly write down what I need to do next without a lot of headache. Bullet journals are implicitly ordered by time. You build them up over time. Every day, you make a new entry, and you kind of record what you do at time. Right? Same thing. We've partitioned all of our data by time in time series databases. However, in a bullet journal, you want to be able to review what you did, and so there's an implicit roll-up period. You have weekly pages and monthly pages. This is just aggregation in a time series database. And at the same time, you have a lot of events that you enter that you want to be able to find later. Maybe you're working on a project. You have events for that project over a number of different days. So what do? You create an index page where you just write down what page number, different events from that were on. That's the same kind of indexing that we do. So all of this database mumbo-jumbo talk doesn't make a lot of sense to you. Just go watch Mr. Ryder or Mr. Carroll's video on bullet journals, and it'll tell you everything you really need to know. I want to talk about four different parts of InfluxDB as we kind of move into some of the Influx internals. I want to talk a little bit about the write path, how this database receives and organizes data. I want to talk about how the database stores data, the different requirements when a point is received to store that data. I'll talk a little bit about querying, and then I'm going to talk just briefly about how the enterprise clustering features work in Influx, like what components are added in the cluster to add high availability and scale out. Are you ready? All right. So for the write path, when you write data to Influx, you basically can just post it to an endpoint. And this post actually gives away a lot about kind of how we think about the system. So first, unlike working with a traditional SQL system, you don't want to have your devices running like an ORM, right, to make it easy for a developer to interact with the database. You want to be able to collect lots of metrics together, right? You want to be able to do some buffering at the client and perhaps provide them as a batch. Right? And you want to be able to collect data from a huge number of different sources, and that argues strongly for a very simple text-based protocol. So you can see all of these design choices even just in this simple post message for Influx. You can just use one of the world's most common protocols, HTTP, send a line of text to the database that's sort of shaped like a metric should look or like a measurement should look, and in doing so you've managed to add a point. So the other thing that's really interesting here about time series systems, or maybe analytic databases in general, is that the person that's inserting data or the program that's inserting data into the database is very often a different user, or maybe even a different organization from the people who are reading data out of the database. Right? So in a traditional SQL system, like in Postgres, the state of your database is really built up by lots of user interactions that are slowly changing data over time. Right? So if I have a database of user profile information, every time I interact with that service, maybe my profile gets updated a little bit to record an action or a purchase or something. Right? So the state of the database is built up by my interactions as a reader and a writer to my record. It's really different in analytic systems where the state of the database is really collected from people who are streaming values into the database, then later on a completely separate group of people are going to read them. This means that the interfaces for receiving and reading data tend to be different. And you can see that in this example as well. The interface for writing data, just this very simple line protocol, makes it very easy for low-power devices or for little scripts that are running on a workstation somewhere or server somewhere, right, to form this data and push it to the database. And then we'll reserve a separate, more sophisticated query interface for the users and dashboards and tools that are actually doing exploration. We don't force both to go through the same path. So when you add data to the database, there's actually three processes that get kicked off. The first is we have to write this point to a write-ahead log. We add this then to some in-memory structures that become the TSM data, and then we add it to an index. I'm going to walk through each of these three processes in turn. So when you write data to the database, the first thing the database needs to be able to do is make that recoverable. So if the node were to crash or the server were to crash, when that server reboots, it needs to have a copy of that batch of data that you just wrote. And so to do that, it essentially just uses snappy compression, and it snappy compresses the batch of data that you just sent, the data that was in that post request, post method, and it writes that to a journal, just writes it to a write-ahead log. Then if the server is to crash, it can read that write-ahead log back and essentially just replay those points as if they'd just been sent. So there's like the little batch of points of time before that data's made it into a TSM file, which is the long-term storage format, that those points exist on disk as a write-ahead log. So compressing that batch, handing it to the log, f-syncing the log, right, making it durable on disk is a fast and cheap operation. But the wall would be useless for query, right? Just like this is make it easy to write, difficult to query, right? Back to the earlier trade-off. So in this case, we don't want to read the write-ahead log for query. This is just a bunch of points in any particular order that the user chose that we've compressed into a format that can't be arbitrarily indexed into. This is really read-only data effectively, and it's only read on recovery. So we also write the data to what we call an in-memory cache. Now, a lot of analytic systems that are columnar in nature will use a slightly different terminology here, which you might be familiar with, but they often have an in-memory row store and then an on-disk column store. Or some people will call it a write-optimized store that's in memory and a read-optimized store that's on disk. So this add to in-memory cache step for Influx is essentially how we add data that we want to prepare to store into long-term storage. And I'll speak about the indexing separately. So when you can actually see the artifacts, of course, on disk. Influx stores data in a nice sort of organized way. When you define a retention policy, right, you set a duration, a replication, a shard count, and the database then goes and lays out this file directory, this file structure. So there's a database directory. Within that, there's a retention policy directory. There's a logical concept that's not represented on disk, but that's important to the database called shard group that we'll get to. And then there's a shard directory. And a shard is kind of assigned to one of these logical shard groups in the system. And that shard directory finally actually contains the data. It contains these TSM files, which we'll talk about in some more detail. So we've received a point. We've made that point durable for recovery by writing it to the write-ahead log. We've kind of stored it into this in-memory cache. Our goal is to organize it and get it onto disk into this read-optimized format called TSM. So what's a TSM file look like? so a TSM file, I've been talking a lot about columnar storage. Again, another kind of raise hands. Who knows the difference between like a row store and a column store in database land? Is this like familiar? No? Okay, so let me describe this briefly, I think, and then it make a little bit more sense. So a traditional database stores records in row orientation. So it might store like Ryan, Betts, like Massachusetts, where I live, right, and my date of birth. And then it'll store, you know, John Smith, New York, where John lives, and John's date of birth, right? So each record is contiguous on disk. My full record, then John's full record. This works really well if you want to transact, if you want to perform ACID transactions against a particular record, because the database just needs to find that record and it can then read your entire record or your entire user profile, whatever it is, right, into the query portion of the database and manipulate that. However, it really works quite poorly if you want to be able to run an analytic query that crosses many, many records. So in practice, records and databases tend to be very wide. It's not unusual for a database to have 100 to 200 columns for what might seem at first like a simple table, but there's a lot of attributes that we want to remember for each entity in the database. And so those attributes turn into columns, those records become very, very wide. Most analytic queries aren't interested in processing the entire record. What they really want to do is take the average, or maybe they want to calculate how many people live, you know, count by state. Right? Well, if I have a billion users in my database, or well, maybe 300 million users in my database, and I just want to count who lives in what state, well, I don't want the database to have to read all of the other columns that aren't relevant to that query. So what columnar systems do, and these are systems that are more focused towards supporting analytic workloads, is instead of storing data in a row orientation by, you know, my entire record and the next entire record, they store the data organized by columns. So on disk, the order of data would be like Ryan, then John, then Betts, then Smith, then Massachusetts, then New York, right? So the columns are what's contiguous on disk. That means that when the database wants to do something like count users by state, all it has to do is find where the column starts, right? And it can just read just the states, and it can aggregate them as it goes. And then you don't have to do disk reads for all the other data that's not relevant. So it turns out that optimizing disk access is, of course, one of the key things of making a database go quickly. And if you cannot read 199 of the 200 columns in your database, then you can become proportionally faster. Another advantage to storing data in a columnar fashion is that it compresses really nicely. So for example, there are only 50 states. Maybe we'll adopt Puerto Rico someday soon. But for the moment, there's 50. And so if you put 50 states, you can just order them, right? Well, here's everyone who lives in I don't know, what's the first state alphabetically? Alabama. Thank you. Yeah, right. And then Alaska, perhaps, kind of in order. So, and now, of course, if I have 300 million people, I don't need to write down the word Alabama however many 10 million times, how many people live in Alabama. I can write the word once, right? Just remember that it corresponds to 10 million other records. So already I've saved myself the overhead of storing the string Alabama almost 10 million times. So these are some of the benefits of storing data in columns, and this is what Influx does. So when you see a TSM file on disk, it's a binary file, but it has a very regular structure, and it's not too difficult to understand. So this chart starts from the entire file, and then it breaks down the interior components of it. So the TSM file itself has a short header just saying, hey, I'm a TSM file. It contains a lot of block data, which is basically the table data. It contains an index. This is a different index from the query index that you're used to. So the TSM index that basically says where do different blocks start within this big file. And then it contains a footer with some metadata that's necessary to make things efficient. Each block then, so there's this big range of blocks. Within that big range of blocks, there's many blocks, and each block is just a little bit of data, right? And so each block is essentially a column from a measurement. And then within the block, you can see that the two columns that are stored for every measurement are its timestamp and its value. So of course, a measurement or a series has a lot of tags and other things that identify it. We don't repetitively store that over and over again for every value. Instead, we basically use the index to understand that this block stores values for this particular series, right? And then we can use kind of well-known compression techniques to make it cheap in terms of disk space to store those timestamps. So timestamps are incrementing. You don't need to store them over and over again. You can kind of more or less just store the bits that change with every new timestamp. and a lot of cases, values are repeated. So for example, if your metric is just, is my server healthy or not, right? Or has there been an error? You're gonna get a lot of repeated values, like 0, 0, 0, 0, 0. Oh, there were 100 errors, 100 errors, 0, 0, 0, 0. You can do run length encoding and other simple compression techniques there. And so you can actually take a large amount of data you have and make it quite small. So if you've ingested large amounts of line protocol into Influx, you can have some idea for how many gigabytes of line protocol data you have. Then you look at the storage system and you see that the files on disk are quite a bit smaller. These are some of the techniques that make that data smaller. Then within the index is basically metadata about these blocks. So what type of data is in a block, how many records are there, what time span does that block cover, where is that block in the TSM file, et cetera. So when you want to come and find data in a TSM file, the engine will first understand, we'll talk about how the query engine works in a little bit, it'll understand like which files to access, it'll look at a file, it'll read the index, and it can read that index basically to find the offset for where a block is in this file. Then it can go and read that block and read a very efficient representation of a field in a time range. So we kind of walked through a little bit about what happens here. You receive a point, you kind of write that point and it's batched to disk so that if the system were to crash immediately, you could just replay that essentially as if it had replayed from the client. We build up an in-memory state that represents sort of the recent data that we've received that's efficient to update. These TSM files are immutable. Once they're written, they're not alterable, right? They're just only there for read. And so we gather this data in an intermediate stage in memory in a way that's kind of write optimized, it's easy to mutate. When that cache fills up, it kind of reaches its target size, we then write that data to the first TSM level. Like TSM files will be combined and kind of recompacted together. So we write the first level of the TSM file from that in-memory cache. And now that all of the data that's in memory has been written to a TSM file, we no longer need the data that's in the write-ahead log. And so the write-ahead log is the durability mechanism for this in-memory cache. Once the in-memory cache gets flushed to TSM files, then we can truncate the write-ahead log. Otherwise, it would grow forever, right? It would consume too much space, and it would make recovery take far too long. So that's basically how we receive data, make it immediately durable, organize it in memory until we have enough to efficiently write out the first structure on disk, and a little bit about how those structures on disk are organized to make it cheap to read long scans of sequences of a field. So hopefully I've managed to explain that a little bit. But we still haven't described how querying works at all. Right? How does the query engine actually work? Well, there's another index, and this is separate from the TSM index, but there's another in-memory index that many of you, if you're users of InfluxDB, might be aware of, because it's one of the primary sizing characteristics of the database. So currently, we store every series has a number of pieces of data that are stored in memory. And so as your cardinality of series increases, the memory consumption of the system also increases. So a lot of people kind of discover the in-memory index as they see memory grow in their system as they increase the cardinality of their series count. So the in-memory index is really just a lot of different maps. And these maps exist to make it easy for the query engine to locate shards or ranges of TSM files that have data that's appropriate to a query. So we map measurement names to the field keys of that measurement. We map measurement names to the series identifiers, and names to values, keys to tag values, to series to shards. Lots of different mappings so that when a query executes, we can read the query and very quickly identify which shards and which time ranges and which series and which measurements are appropriate or necessary to read to satisfy that query. We've also started adding some probabilistic data structures like hyperlog log sketches to make it to track cardinality and some other metadata aspects so that we can make it very cheap to query cardinality of the system without needing to go and visit every series and count them manually. So the traditional index in InfluxDB has always been an in-memory index. For about the last year, we've been working on an index that can store some of this index data on disk as well. And I don't want to walk through the details of TSI too much here. We'll be writing about this and showing some more performance benchmarks as we go forward. We have a publicly available release candidate now for 1.5 that includes TSI work that we're going to support in production workloads. Previously, we had shipped it as sort of a technology preview. But I'll talk about it a little bit and kind of point out how it differs slightly from the in-memory index. So how is it the same first? So it's the same as the in-memory index first in that it stores essentially the same mappings. However, it stores these mappings on disk, and it uses a very similar kind of log-structured merge tree idea as the TSM data that I just showed. So the TSM data is written to disk. It's immutable. If you want to write more, you can append some data. If you want to, we'll talk about deletions later. You can then, once you've written a lot of data, you can kind of combine it into more efficient blocks. The indexing file for TSI works kind of similarly to that, and it includes two different types of data that get stored on disk. One is a log of activity to the index, so add a series, delete a series, add a key, delete a tag, add all the different mutations that can occur to the series that are being indexed. And then the other is a per shard, the index file then is actually the mappings themselves, right, that can be persisted to disk. There's a lot of kind of fancy data structures that are used to make this efficient. So the index, every time you create a new series, that series needs to be inserted into the index, and mappings need to be created for that series so that you can understand which fields and keys and measurements and tags correspond to that series. And so adding a new series to the index is expensive, so we keep a bitmap of indexes, or a bitmap of series that are already present to make that cheap. There's a lot of technology here to kind of walk through, and we don't quite have time today, but I'm happy to answer questions at the end. But the core thing to take away is that the TSI index maintains the same mappings as the in-memory index, essentially, and that it allows some of those mappings to be persisted to disk. It persists those to disk using a log-structured merge tree format that has some of the same readability, efficiency benefits, and compaction benefits as our time series storage. So we've started running TSI on some of the shadows of Influx Cloud clusters, so we have the capability of essentially cloning Influx Cloud users and then running their workload in the background on another cluster. And you can see that, I guess I call this like the TSI doesn't suck slide. So the arrows are pointing to like the reduced memory utilization and the reduced CPU utilization of TSI. The higher memory utilization is a cluster that's storing all of its data in memory, so that's to be expected. Some of the CPU spikiness comes from other optimizations that have just occurred over the 1.5 release cycle. So there's two different examples here of two different clusters running in Influx Cloud that have been shadowing this work to TSI in the background. So a little bit about InfluxQL. So when you write an InfluxQL query, I think this hopefully can kind of build up to this, like we've talked about how data is ingested, how it's made durable, how it's organized on disk in a way that it makes it efficient to read. So now this is just the activity of understanding a question the users asked, finding the data that you need to read in order to answer that question, and then producing the answer. So when you submit an InfluxQL query, essentially it parses that query into the time ranges that need to be accessed, into the expressions that need to be applied to data, and into the groups that have been requested. It uses the indexes to find the shards in order to access the correct measurements for the correct time frames. And then it creates iterators for each of those per measurement, per shard accesses. And it just pulls data out of the shards into these iterators and processes them, and can merge iterators, create the difference of two streams of iterators, create the union of two iterators. That's essentially how the query executes. There's a couple of things that are interesting. So coming from a SQL background, there's not a lot of opportunity for users to optimize a query in Influx. So you can't, for example, define a new index or hint to the database about how it should store data. So anyone who's done a lot of SQL query optimization as a user kind of understands the set of tools that are available to them using their domain knowledge to hint to the database about how it should execute a query. And what you see in this system is it doesn't quite work that way. Instead, the system has made it easy to locate where a series is located on disk, and it's made it as efficient as possible to read that. And it basically then just reads that data and merges it into a graph of iterators and operators. So IFQL works from some of the same principles, but has a number of key differences that I want to highlight. So first is IFQL has the option of having a standalone coordinator node. This means that you no longer have to share the memory of a storage node with the memory of a query node. These are really different workload behaviors. Storage nodes, we really don't want our storage nodes to burst in memory a lot. They do sometimes still when they have to do a large compaction, but you really want a storage node to have a very predictable memory utilization. It makes it easier to operate, easier to understand if it's operating correctly. However, some queries can take a large amount of memory to execute, right? And so you'd like to be able to give those queries their own memory, their own RAM for that execution. And you especially don't want to have perhaps a spike in storage for compaction collide with a query that needs a lot of memory. These become very difficult resource management tasks within the database. Another difference with IFQL is IFQL supports only support streaming storage iterators that support rate limits. So the database exposes an interface that allows an IFQL query to push down an access path, like I want to read these series for this time range filtered by this value or windowed in this way, and the storage engine will just stream that data out. It doesn't have to buffer that data anywhere. And that stream has a rate limit concept so that we can start to get fairness across tasks or have high priority tasks and low priority tasks, right, to basically do better resource management on the server side. These are all features that just because of implementation reasons were quite difficult to do in InfluxQL. And then, of course, finally, the features that Paul talked about is from a usability perspective. It's functional and allows the unification of Influx and tick script. I actually was going to talk about this a little bit more, but I think Colin presented this so much better than I did, that if you read a lot of database papers, you talk to a lot of academics, you think about how to productize database research, no one ever tells you that these databases are append mostly, and it's the mostly part that's really nasty. So databases tend to get wrong data for two reasons, and these time series databases that are optimized towards read, that have done all this work to organize immutable data nicely on disk, every now and then you have to kind of go delete it, and you find that you have to delete it for two reasons. One is someone get you the wrong data, right? The user made a mistake, sent you data they don't want, and they now need to go delete it. You need to undo all of that beautiful work you did to organize this data, find some efficient way to eliminate the bad data, and then recompact all that into readable formats. That's a pain to do efficiently in a way that's friendly to users and predictable. Or people come with old data. So we've kind of had this idea that we can kind of marshal data into a readable format over time, and all of a sudden someone comes along and says, oh, remember last month? I have some data from last month, and I figure out how you're going to take that and merge all of that back into those legacy systems. So there's some aspects of operational difficulty. I'm running a little bit long, but I think I have 2 more minutes, so I only have a couple more slides. So I want to talk a little bit about clustering. The clustering from Influx is really very simple. The easiest way to think about it is that we add just a few components to the open source database, and we use those to kind of gain scale out. So the first thing we add is a strongly consistent meta cluster. It's just a cluster that uses RAF to maintain a consistent view of where shards are located, essentially, on the storage nodes. This is really just a directory of which storage nodes have which data, is the easiest way to think about it. We allow the users to specify a replication factor, because once you have more than one server, you probably want to store more than one copy of your data. And then the query planner becomes replication and shard aware. So it understands, by using the metadata that's cached from the meta cluster, which shards it needs to contact that might potentially contain a series, and it has the ability to distribute access to data across the cluster, pull the results of that back to whatever storage node happens to be coordinating the query, and then merge the final results. And then there's 2 attributes here to try to maintain consistency within the cluster. One is a hinted handoff queue, meaning that if a node receives a write that it can't replicate immediately, it just writes it down on disk, waiting for the node that couldn't be reached to come back, and it can replay that write at a later point in time. Hinted handoff is a really common technique in distributed databases that are eventually consistent. And we've been putting a lot of work into an anti-entropy repair, consistency repair, which basically is an algorithm that can look at fully compacted TSM data, which is relatively deterministic on disk, summarize the data that are in each block, essentially kind of hashing the blocks, you can think of it that way, exchange those hashes and find blocks that mismatch when they shouldn't. Then we can make partial repairs within the cluster for that. This is work that's in progress. So a couple of conclusions. One is that I hope that everyone kind of agrees that time series data is unique, right? That what we want to build for a time series system is a little bit different from a relational system. It's a little bit different from just an eventually consistent NoSQL system. There are trade-offs that can be made that are appropriate to this domain that create a database that's much more powerful and efficient and fun to use. And the second is I want to kind of highlight some of the things that sort of were evolving about InfluxDB. I think we talk about a lot of these things individually, but we rarely get a chance to kind of talk about them as a whole. So I kind of think of this as bigger, better, and more correct. These are kind of the 3 major engineering efforts that we're working on right now within the storage and query teams. So TSI allows the database to store more data at a higher cardinality, right? It's all about being bigger. IFQL allows more expressive queries, allows us to be more responsive to the community, allows us to remove some of the unpredictability that large queries can cause in a cluster, right? Those are all better. And then anti-entropy repair is something that allows us to become more correct over time and repair consistency efforts or consistency differences in the database. So thank you very much. I apologize for using a couple of minutes too many, but I appreciate the time, and thank you. Take a question.
You mentioned that you're using Hyperlog for cardinality. For percentiles, are you using tdigest or something percentiles? Are you using tdigest or actually either a way to get percentile data?
Okay, so do you mean when? Yes, I think I understand your question. So we are shipping the ability to use tdigests for query percentile. So if the user wants to know percentile, we'll be able to give them an estimated percentile. That's a feature of IFQL that will be shipping. Primarily, the use of hyperloglog within the structures that I discussed are to make it very cheap for the users to query cardinality. So commonly users want to know, because controlling cardinality in these time series systems is important, users want to know how many series are in my database. We want to make that as close to a constant cost query as possible. And so that's where we're using hyperloglog sketches to enable that meta query about cardinality in the database.
Are you guys using Bloom filters at all?
No, so we haven't used Bloom filters for these purposes. We've maintained bitmaps in some of the sketches, but I don't believe there's a Bloom filter in TSI. I could be wrong.
I think there actually is.
Is there?
Yeah.
Okay.
Ben added that, yeah. He added it at one point. I'm not sure,
if
it's still there or not to dig into the code.
Trying to figure out how to efficiently maintain the metadata that TSI needs to maintain while not slowing down ingest and series creation has really been a deep engineering challenge, and there's been a lot of attempts. Well, we'll have to look.
Yeah, the Bloom filters are basically there to, when you do a query against a tag key value pair that actually doesn't exist, the Bloom filters are there to avoid like going in. At least I think that's what I saw from Ben's
all right.
stuff.
So I think you win I think you win points for Stump the Geek today. It's good. So.
Woohoo! Sorry, I got one more.
How do you shard the data? What function do you use, and what's the inputs?
How do we shard the time series data? They're basically just like hashed into shard groups, right? So there's nothing. That's a hash of the series ID, right? So it's the measurement, the tag set, the fields. So it's really uninteresting.
Doesn't that mean that queries have to touch every single node?
Yes.
Right. Okay.
Yeah. Which is a really interesting trade-off. But they understand. They can understand. By the time they have to go read data, they understand which shards might have a series or not. So they can skip shards that don't have a series at all. They can use the indexing for that portion. But yes, many queries touch a lot of nodes.
Oh, is the index sharded differently to the actual time series data?
No. But the index is referenced on the access path. So when the query is distributed, it gets distributed to the node. It'll look at its local index and understands if it needs to go to disk.
Right. Okay. Thank you.
Great.
All right.
Thanks, Ryan.
I'll catch up with you later, Jim.